Hello everyone, and in this video I am going to go over experiment 2 with you. Okay, so experiment 2 is on measurements, the metric system, and density. So there are several objectives for this experiment. We would like you guys to become familiar with the metric system by taking measurements using metric units. So as you know, the United States is one of the few countries to still use the non-metric system for measurement. So measuring things in like inches, for example, instead of centimeters. But when we are doing science, we're going to be using the metric system. And we want to learn how different measurements are to be taken with different devices, and specifically learning about the precision of each device when taking measurements. And lastly, we want to practice using dimensional analysis to convert one set of units to another set of units using the correct number of significant figures when you are doing those calculations. Okay, so with any experiment, we're going to start with the Prelab. And the first question in the Prelab is looking for you to get a little bit more familiar with metric conversions. So as you know, there are different types of units, for example, meters or liters, right? Grams, things like that, depending on if you're measuring mass, if you're measuring the volume of a liquid, right? Or if you're measuring some distance. And then there are often these prefixes involved where it might not be a measurement in meters, for example, but instead of that, centimeters or nanometers, for example. And the same thing could be true with other units. You could talk about milligrams, right? That's a common one. So it doesn't matter, what the metric unit is. For example, like grams, liters, meters. We still want to be familiar with these prefixes that can be used interchangeably. And so this part is asking you to really think about some of these prefixes. So we want to be familiar with the fact that some of these are actually smaller than just the meter by itself. For example, decimeters, right? There are 10 decimeters in a meter. There are 100 centimeters in a meter and 1,000 millimeters in a meter, right? And you get the idea, and so on. So there are a million micrometers, right? A billion nanometers in a meter. And so this is really asking you on this side, right? All of these units are actually smaller than the meter. And so if we have 1 times 10 to the 9 nanometers, right? And then there's 10 to the 9 nanometers in a meter, how many actual meters is that? So I'll give you a little clue. The answer to all of these is actually the same number. So it's not meant to be very confusing, right? It's just trying to get an idea of how many of these are in a meter. And then over here, we have different prefixes that are actually larger than a meter. So the numbers or the answers here will be larger than 1, right? So for example, there are 1,000 meters in a kilometer. And so you can use this, the scientific notation, right, to actually know how many there are, right, in that meter. So, and then if it's, a larger number, then there's actually 10 to the 3 of the meter in the kilometer. So that's the way to read that, or 10 decimeters in a meter, if it's a negative over here. So you can enter these values in scientific notation when you're in Canvas, or you can enter them without scientific notation. So for example, if the answer to this first one was 1.0, you could enter that as 1.0 or 1.0 e to the 0, which is the way to do it in scientific notation. So here are some other things to remember with scientific notation. If you see the little decimal point, that means that this 0 is significant. If the decimal point wasn't there, the 0 would not be significant. So if it's significant, then we're going to include it with the number in scientific notation. So this would change to negative 4.60 times 10 to the 2, which we just input with an e to the 2. We can also do negative exponents, right, with the system where we replace the times 10 to the with an e. For example, if your answer was 0.4797, you would move this decimal to the right and we would be at 4.797 e to the negative 1. So that's how you would input it into Canvas to make sure you're getting the correct answer. Okay, and this is the next part of the Prelab. So in question number 2, it asks you to do some conversions between reading temperature in different units. So for example, we can read them in units of Kelvin, which is represented by this K, degrees Celsius, which is represented by the C, or degrees Fahrenheit, which is the F. So these are different equations that you can use to convert a number, or in this case, a temperature measurement from one unit to another. So if you wanted, for example, to convert to Kelvin and you were in degrees Celsius, you would take your degrees Celsius, add 273, and that would be the value in Kelvin. So this is practicing converting between the units of Kelvin to degrees Celsius and degrees Fahrenheit. Just pay attention here to the number of significant figures. So this is 0.00, right? So they did these 0.00s on purpose, right? That's supposed to be letting you know that you should report your answer in 3 significant figures. Whereas 105.0, these two numbers then should be in with 4 significant figures. And in this section, you can input all of your answers in scientific notation, right? So if your answer was negative 273, you could input it that way, or negative 2.73 times, or just e and then 2, right? So to be consistent, I would just recommend inputting all of the answers in scientific notation, even if it's writing E0 at the end, which seems kind of redundant or not necessary. Just to be consistent, that answer will be there as well in Canvas and will be marked correct. I just point this out because I noticed in Canvas it says 4.00, not 4.000, which is what it says in the worksheet. So when you're inputting it in Canvas, just go ahead and only use 3 significant figures for the milligrams and the grams. To do these unit conversions, you will need the appendix. So I just put a picture of it here, but it's also in the lab manual. And so you can use the appropriate conversion factor, right, to convert from ounces to milligrams. And then remember, there's 1,000 milligrams in a gram, right? So we can practice converting between metric units with different prefixes as well in this section. Notice 4 significant figures here, so go ahead and report your answer in quarts and liters to 4 significant figures. Again, convert everything to scientific notation. It's just kind of common good practice for you here. All right, so once you're done with the pre-lab, you can think about starting the experiment. And I want to really emphasize that this particular experiment is compared to, let's say, the other experiments. This one is, arguably the most important experiment, because not only are you going to be working towards your 50 points for this experiment, but also both practicals in this class are based on what you learn in this experiment. So the first practical is 25 points. The second practical at the end of the semester is 50 points. So really, you're working towards 125 points total just on what you're going to learn in this experiment. So this is really, really important that you understand how to read these measurements to the correct level of precision, understanding which numbers, where the uncertainty is in a measurement, and how that relates to significant figures and how you should record your measurements. And also don't forget always recording your units. That's super important. Okay, so emphasis in this lab will be on the proper use and reading of each measuring device. Each one will have a different level of precision, which means you'll be recording it to different places, different decimal places. Like in some cases, you might record to the tenths, right, or to the hundredths place. And so it's really important to know when and how to do that properly. And then also we will be practicing unit conversions through dimensional analysis in this experiment as well. Okay, so how do you know, right, the correct precision when reading a measurement? Well, it has to do with the device that you're using to record that measurement, right? And the precision is related to the graduation, which is the same thing as the hash marks. So it's related to the values in these hash marks or the calibration of each measuring device. And so what you want to take away from that, right, is there's sort of two distinct possibilities here. And really in this experiment, we'll only be looking at the first one. So all of your measuring devices the graduation will be what we call the delta value, and I'll explain that in a little bit, will be 1, 0.1, or 0.01, right? And then the precision is 10% of that graduation. If you were using a measuring device, which again, you're not going to do in this particular experiment, but we're going to teach you about it anyway. If the graduation or hash marks were every 2, for example, milliliters, or 0.2 or 0.02, then the precision is 25% of the graduation. And I know that these words that I'm saying to you right now don't make a lot of sense, but as we go through these examples, you'll see exactly what I mean when I say the precision being 10% of the delta value. Okay, so let's look at, so let's talk about the measurements that we're going to be running in this experiment. So you're going to run measurements using a lot of different measuring devices. We're going to use a thermometer, and we'll measure in degrees Celsius with that. We are going to use different size graduated cylinders. Those measure volumes in milliliters. We will use a ruler. And when we use a ruler, you're always going to use the metric system. So typically you'll be measuring in centimeters, right? So these are a variety of different measuring devices. You'll also use a scale to measure mass. And they each have different levels of precision based on their calibration, their graduations, or their hash marks, right? So what we have to do is look at the difference between two consecutive hash marks. And this difference is called delta, right? So let's look and see. Okay, so this is a ruler, right? We're measuring in centimeters. Let's say we were measuring something, right? And we can tell it's more than 4 centimeters, right? But not quite 5 centimeters. But we actually have hash marks in between these two numbers as well. And if we count them up, right, there's a total of 9, meaning we've broken this up into 10 pieces, right? So we can measure 4.1 centimeters, 4.2 centimeters, 4.3 centimeters, and so on, right? So what is the delta value, right? Well, it's the difference between the two hash marks. So we're reading to the 0.1, right? Because 4.1, 4.2, what's the difference between those numbers? It is 0.1, right? So that's the delta value. And then your precision or your uncertainty is 10% of that delta value. So if your delta is 0.1, then your precision is plus or minus 0.01, because 0.01 is 10% of 0.1, right? So you can see I have it measured over here, or I have it written down over here. So our delta value is 0.1. Again, that's the difference between the smallest hash marks that we see here. The precision is then 10% of that. So 0.01 plus or minus 0.01 centimeters. So how then should I record a measurement, right? You would want to record in this case to the nearest hundredth. So let's say we had some item, right? And it was past the 9 centimeter mark. It looks like it's past the 0.5. But it's somewhere between 0.5 and 0.6. And obviously we have to estimate that last number, right? If my, whatever I'm measuring is between the 0.5 and the 0.6, I need to measure or estimate to that hundredths place, right? So if it looked like halfway between 0.5 and 0.6, I might say 9.55 centimeters. Or if it was a little less, maybe my eye, says it's, well, maybe it's about 9.53. You get the idea. But the really important point here is that you have recorded, right, 3 significant figures. So if you record using this ruler and you just write down 9.5 or 9.6, then that is not measuring it correctly to the correct number of significant figures. Because the significant figures in the measurement includes that last number, which is estimated, right? That's where our uncertainty lies. So we can see that the item is a little bit more than 9.5, but not quite 9.6. So we need to estimate, right, a number in that hundredths place. And that is actually, that uncertain number, right, is still considered a significant number, right? So we include it with our significant figures. And because our eye can roughly break apart between those hash marks into 10 equal pieces, right? And we say it's about 9.55 centimeters, for example, we have that uncertainty in that last number, right? And it's going to be typically about plus or minus 0.01 centimeters. So again, our uncertainty, right? Maybe it was actually 9.56, right? Or somebody else would have written 9.54, right? But again, that's where our uncertainty is, and that's okay. We're still going to include that number that's uncertain. It's still a significant figure. All right, let's talk about other measuring devices that we're going to come across. What about this 100 milliliter graduated cylinder? Well, it's important to note that there's 2 sets of numbers here, right? Where the numbers are sort of going up from 0 to 100, right? Or the opposite direction. We're going to read volumes from the bottom up, right? So if the liquid was up here, we would be reading, 80 something milliliters. Okay, if we look at the hash marks here, so you can see there's a big line every 10 milliliters, but then under that there are we have these hash marks as well, like, so this would be 61, 62, 63, 64, 65. You get the idea. So the delta is 1 milliliter because the hash marks are at every 1 milliliter. So then the precision is 10% of 1 milliliter, which is 0.1 milliliters. So when we read the volume here, we are going to be writing down a number all the way to that 10th place, right? So you may be, depending on where the bottom of the meniscus is, that's what you read, right? And you want to be eye level with it to get a correct measurement. You would maybe read 84.0 milliliters, but you don't write 84, right? You have to write 84.0 because we're estimating that last number, right? We can see every 1 milliliter, but there's also space in between those hash marks. And so we estimate in that space, right? So it's above the 84, right? And it really almost looks like it's exactly at 84, then you would write 84.0 milliliters. Okay, let's look at this thermometer, right? That's being measured in degrees Celsius. So we can see there's some red alcohol, right? And it's rising up here, and we're going to take a measurement. Well, if we look at the hash marks, right, we see that this is 10 milliliters, and then this is 20. So this is 10, 11, 12, 13, 14, right? And then this would be 15. So the delta, again, is at 1 degree Celsius, because that's where we're reading, right? So 10, 11, 12, the difference between 11 and 12 is just 1, right? So that's where that delta comes from. And then 10% of 1 degree Celsius is 0.1 degrees Celsius. So we need to read to the nearest 0.1, right? So we can see that it looks like it's above the 14, but not quite at the 15. So we would read 14 point, and then you estimate roughly where you think it lies between those two hash marks, right? So I thought it was about 14.3 degrees Celsius, again, plus or minus 0.1 degrees Celsius, because again, most readers can sort of break apart that distance into 10 equal spots, right? So we can read to the nearest 0.1. Plus or minus, I should say, 0.1. Okay, so here's an example, and you guys, again, are not going to run into this because KLM has provided you with graduated cylinders, and the difference, the delta value, is always going to be 1 or 0.1. So you will always be measuring plus or minus 0.1 or 0.00, or so sorry, I can say this again, plus or minus 0.1, right? Or which would be milliliters, because we're measuring volume in this case, or 0.01 milliliters. So, but sometimes you might run into a measuring device where the hash marks are not at every 1 milliliter or every 0.1 milliliters, but instead might be at every 2 milliliters or 0.2 milliliters, right? So if you're taking a measurement and your delta is 2, or for example, 0.2, right? Like we would see over here, then our brain can only really estimate, right, 4 chunks in between those hash marks. So the precision is actually 25% of the delta value. So let's look at this volume, right? So we can see that there's a line here at 5, right? There's another big line here at 10. And then we have these other lines at 6 milliliters, 7 milliliters, 8 milliliters, 9 milliliters, right? So, and then in between these, and we can say this is in between 7 and 8 milliliters, there are additional hash marks, but we're not breaking it down into 0.1. Instead, it's 0.2, right? This would be 7.2, so 7.0 right here at the big line, then 7.2, 7.4, 7.6. And so it looks like it's somewhere between, right, 7.4 and 7.6. So again, because it's 0.2 in here, right, we can't really get as fine precision. So we're a little bit more uncertain, more like 25% of that 0.2 instead of, we were at 10% before when our graduations were at 0.1. So we would still read the measurement to the nearest hundredths, right? So, but again, it's going to be not, so you wouldn't write like 7.49, for example. You might write 7.45, 7.50, or 7.55, right? So that's sort of what your brain can measure between these two hash marks. Right here would be, again, 7.4, and this is 7.6. So depending on where this line is, and you have your eye, it's at eye level, right? Maybe you would go with 7.45, 7.50, or 7.55, right? And then it's plus or minus, now in this case, 0.05, because that's 25%. I forgot to change this number. I'll change it in the PowerPoint slides. 25% of 0.2 milliliters is 0.05 milliliters. Okay, we are also going to be measuring mass using a digital scale, a little pocket scale. And you guys should have these, and hopefully you've already checked to make sure that yours is working, right? When we are reading using our digital scale, we want to make sure that we're reading in grams. And you'll see a little G here, which will indicate that it's giving you a value in grams. All the digits that are shown are significant, with the uncertainty being at the hundredths place. And it actually tells you on the scale that the graduation is 0.01 grams, right? So plus or minus 0.01 grams. And that's because this value changes by 0.01. So when you measure something, you might see it fluctuating a little bit between like 2.54 grams and 2.53 grams, right? So it goes up or down by 0.01. So that tells you that the level of precision is plus or minus 0.01 grams. If this last number changed by 0.05, meaning it will fluctuate a little bit on some scales where you might measure your mass, right? Some scales do this, where it's like 130, pounds, and then it'll say 0.5, and it will only change every 0.5, right? So maybe it's 130.5, then it might go up to 131, then back to 130.5. So you can see in that case, right, there, the uncertainty would be in the 0.5. So if this one changed every 0.05, meaning maybe it weighs 1.05 grams, and then it goes up to 1.10, then back to 1.05 grams. If it was changing in increments of every 0.05, right, then there would be a precision of plus or minus 0.05 grams in that case. But in our case, it's going to be 0.01 grams. So when you are recording a mass, right, you want to write down all the numbers that it shows here. All of them are significant, with the last number in that hundredths place being where the uncertainty is, plus or minus 0.01 grams. And then I wanted to point out, and I'm not going to be able to show this very well, unfortunately, because when I got home, I found out that my scale doesn't work. So I'll have to get another one, right? But you would open it up and turn it on. And mine doesn't, I couldn't get mine to turn on, so I don't think it's working. But anyway, hopefully yours would turn on, right? And then when you are using it, use a weigh boat with it. So you want to put the weigh boat on there, press tare, right? And the instructions are actually up here. You can read about how to do that. The tare will take the weight of the weigh boat and set it to 0. And that way, anything you weigh on here, it will not be including the mass of the weigh boat. But we do this just to protect the scale. So for example, once I press tare, this would read 0.00 grams, right? Then I could measure the mass of my plastic cube, for example. So no matter if you're just weighing like a graduated cylinder or something, it's always best to use something to protect the scale. Okay, so coming back here. All right, so let's move on. Partly in the data, it asks you also to make estimates. So for example, it might want you to estimate the mass of your scientific calculator. So you don't want to weigh the scientific calculator. So don't weigh it, right, to make an estimate. You just want to guess. And one way to do that is to kind of compare it to something else that you might know the mass of. For example, you've already measured a 100 milliliter beaker. So let's say you kind of put them in your hands, right, your calculator, the beaker, and maybe they're about the same, right? And you know that your beaker weighs, 42.41 grams. Maybe then you say, okay, the calculator is about 40 grams. Or if it was a little more, maybe you would say it was 50 grams. But you're not going to write down 42.56 grams, right? Because there's no way you could estimate to that level of precision. So just make sure that you are, really you only estimate like one number, right? So you're not going to have a lot of significant figures here. You should basically have one significant figure, unless you're really good at estimating, but never like to the precision that it would be if you actually measured it, okay? So that's the idea. So kind of compare it to something you might know the mass of and just try to make your best guess. We're just looking that you write something down that doesn't have the same level of precision as if you actually measured it and is like somewhat reasonable. Okay, don't forget to include the photos when you are uploading your data sheet. And in every single picture, you need your student ID or your redacted, other California ID, such as a driver's license, for example. So there needs to be 5 total photos. And then in the lab manual, I think it still says your cube. But we could go ahead and replace that with the evaporating dish. So we are using, there was a little bit of changes, and not every single place where the word came up did we actually manage to change it. So so just, change that in your lab manual to say the evaporating dish instead of the cube. Okay, so there's 2 parts to the experiment. The first part is taking measurements using the metric system, again, using different measuring devices. So we'll start with the mass of various items, like your evaporating dish, 100 milliliter beaker, and 10 milliliter graduated cylinder. And early on in the manual, there's a picture of what things look like, or you could always Google it in case you don't know what one of these items is. I just want to point out that when it says magnitude, just go ahead and write the number, right? The value of the measurement, again, to the right number of significant figures. And then you don't need to write plus or minus, right? So you might just write 14.45, right? And then over here in units, you would write grams, for example. Because I'm down here thinking about mass. And temperature, right? The units you should be measuring in are degrees Celsius. So this is the number, no need to include plus or minus. And then this is where your units go, right? And then your estimate on the last one. So we'll take several measurements using a thermometer to measure temperature, right? We'll use our pocket scale to measure mass. We'll use a ruler to measure length in centimeters. And then we also will use graduated cylinders to measure volume. So when you're doing your own height, right, you can use a pencil and like mark a line on the wall or something, and a pencil so you can erase it, right? And then you can use, if you have like a piece of string or something, right? If you don't have a ruler long enough to measure your entire height, you could do it that way and then measure the string, just sort of moving the ruler along. Or if you have like a measuring tape, you can do it that way. But again, you have to measure it in using metric, so not in inches. We have to use centimeters. Okay, and then part 2 will be the determination of the density of an unknown object. And we're going to determine the density 2 ways. Well, the mass of the cube, right? And we're looking for this like little plastic cube, right? It comes in a little baggie called Experiment 2 cube. And mine's pink, but yours might be a different color. And you'll take the mass of that using your pocket digital scale and record that. And then you're going to get the volume measurement 2 different ways. The first way will be through direct measurement using a ruler. So you'll use a ruler to measure the length of one of the sides, right? And because it's a cube, all the sides will have the same length. Remember to record to the proper number of significant figures, estimating right between those hash marks. And so then the volume will just be that number cubed, right? Because it's the same length, width, and height. So that's where they get the cubic centimeters, which is also, by the way, equal to milliliters. So 1 cubic centimeter, in medicine, we call that 1 cc, is equal to 1 milliliter. You'll also get the volume by displacement. So you'll take a graduated cylinder filled with some amount of water. That will be and we'll read that, right? Read the bottom of the meniscus, the proper number of significant figures, record that as the initial volume. Carefully add the cube in there. It doesn't have to go all the way down, but as long as it's below the water, we can take a final volume measurement, and then the volume will be the difference between the final volume and the initial volume. And remember that density is calculated in mass, which is in grams, divided by volume, which is in milliliters. So your number will be one number, like 1.13, for example, and then the units you would write grams, right, slash or over milliliters. So we will compare, the density 2 different ways. And then I just want to mention in the post lab, it says identify the metal, right? I just went ahead and changed that word to material because we used to use a metal cube, but now we're using a cube made of a different material. And so you'll want to identify the material that your cube is made of. And you'll do that using this table that's in your lab manual. And it's based on comparing your calculated density to the density in this table, right? So you will compare it. Hopefully it's very close to one of these numbers, and then you'll figure out what your material or what your cube is made out of. And that way you'll write in the identity of your unknown. Again, it's going to be one of these, right? Maybe it's acrylic, maybe it's granite, right? One of these. And you'll also calculate percent error. So percent error is equal to the absolute value of the experimental number minus the theoretical number divided by the theoretical number times 100. So these are all your theoretical values, and your experimental value is the one that you measured, the density that you measured, and you probably want to use the one that was more precise or gave you more significant figures. And so that's what you're doing in this post lab. And as you continue in the post lab, that starts having you practice mass conversions, right? It's a little confusing here because in 2 different places it says to do the cube, right? And then over here it says the evaporating dish. So we changed the cube to the evaporating dish. So just go ahead and change that verbiage in your lab manual as well. And so whatever your evaporating dish, right, weighed, you can record it right here, and then convert to, so we want to convert to milligrams, right, to kilograms and to pounds. And again, you'll need these conversion factors to get to pounds. And remember your metric conversions, right, to get from milligrams to grams or vice versa, grams to kilograms. So just, and as you remember some of these, as you use them commonly, you might not have to look it up every single time. Like there's 1,000 milligrams in a gram and 1,000 grams in a kilogram. And then you'll want to show your work, right? Cancel out units by just crossing out the units, circle your final answer, just follow the directions on the worksheet. Okay, so that's basically the experiment. Again, the really, really important part is understanding how to take these measurements and recording to the correct value, right? So if you are, you want to be precise with your measurements. Don't just write, it's like 84 degrees Celsius. If you need to estimate to that 10th place, right, then you need to do that. That's what we're looking for. And that's where you'll get the correct answer if you're doing it that way. And you'll lose points if you're not. So it would be like 84.6, right, degrees Celsius. So make sure that you are right, recording to the correct precision and using the correct number of significant figures. And then if you're doing that, that's the main goal of this experiment. As always, I hope that you're working on this early in the week, right? So that you don't you're not working on it Sunday night, because I might not be able to answer your questions and, help you if there's a problem that you encounter, Sunday night. So it's always best to, even though it's not due till Sunday night, to work on it early in the week. That way, if you have questions, you can email me, come to office hours, get the help that you need. That is, really, really important to think about as well. All right, have a great day.